Alright guys, welcome back. This is a video now which is dedicated to the concept of polymerization. So in level 2 you guys covered addition polymerization. So just a quick definition of polymerization, addition polymerization. Essentially what you're doing is, so polymerization is what this video is about. Polymerization. Some people spell it with a Z, some people spell it with an S, depends where you're from. Polymerization, so there's two types. Addition, which was pretty much unique to just level 2. In level 3, they don't really refer to it very much in exam questions. And the second type of polymerization rather is condensation. Condensation polymerization, which is unique to level 3. So I'll just give you a quick definition of addition polymerization and essentially review what you would have learned in level 2. So addition polymerization, just write it like that for short. In this situation you have two monomers joining together, okay, and they join on the basis of the double bonds essentially unlocking and then reforming new single bonds. So two monomers joining, from that you get a large polymer, and there's only one product. So there's only one product in addition polymerization. So the easiest way to illustrate this is just take an example. So if we look at the formation of Teflon, now Teflon is that non-stick plastic or polymer which is used to coat modern day saucepans. And Teflon is made up of the following monomer. So I suppose that would be 1, 2. So 1, 2 terafluoroethene. There probably is a more colloquial name for it, but that would be the IUPAC name. And two monomers, so two of those monomers, those CF2s. I meant to use a different color for the second monomer just to highlight this in the polymer. So let's go with green. So here's the second monomer, exact same unit, so repeating units. And then, as I say, in addition polymerization, this is one of the 6 addition reactions in alkenes, if you remember from level 2. Where the double bond is the focus or the functional group, and these double bonds unlock or open to form your Teflon polymer. So your Teflon polymer then, if I go back to my red, is going to be composed of those monomers with now they have single bonds. So in an addition polymer there are no double bonds present. So if you remember that much, there are no double bonds present in the product of addition polymerization. So this is Teflon. Let's use the green then for the other monomer that would now be joined on. Again, single bonds all the way, and then your fluorine atoms on the sides. What students often forget when they're drawing polymers is that they forget to show that each carbon at the end still has another bond which is going to then join onto another monomer, and that will repeat. So the way we illustrate that shorthand in chemistry is we just put that open bond and draw some brackets around it, and we can put the letter N down here, where N is going to equal the number of repeating units of monomers which make up that polymer. So just to review again, addition polymerization, you have two monomers joining together. The double bond is the functional group in question. You get one product, which is your polymer, and there are no double bonds present in your addition polymer. So you have things like polythene, which is used in plastic bags. You have Teflon, as I say, is used in non-stick pans, polypropylene, etc. So they're addition polymers, and that's a bit of a throwback to level 2. Now there's no real mention of addition polymers in level 3, so the big one in level 3 is condensation polymerization. So let's talk about condensation polymerization now. So new title, second type of polymer, we have our condensation polymerization. Polymerization. Okay, condensation polymerization. So again, with teaching, we try to initially act on what you guys should understand already. When with condensation, the process of condensation is where you take something like water vapor, which has just come from some water that boiled in a kettle, and then the vapor then turns back into a liquid, resulting in the production of liquid water. So a condensation reaction will produce a small molecule like water, and it's not unique to just water. However, you can produce other small molecules like hydrogen chloride or HCl. So a general definition for condensation polymerization is that, yes, again, you have two monomers joining, just like you had before. Two monomers join, but in this case you produce a polymer, so a large polymer, which is your condensation polymer, and you also have a small molecule, which is a byproduct, in this case something we're not interested in. That could be H2O or HCl. They're the two main ones for level 3 to be aware of. So that is one of the main differences between addition and condensation polymerization. So again, we need to look at specific examples of this. Now with condensation polymerization, also the monomers, I'm going to describe these monomers as being two-handed. So this is just a phrase I've coined. Two-handed molecules. So the molecules are two-handed, and I'll explain what that means in a second. Okay, so these two-handed molecules, there are four main types of polymers, condensation polymers, that are mentioned in level 3 chemistry. So what I'm going to do is I'm going to just dedicate a different page to each one. So if I just get rid of that, so a new page, the first type we're going to look at is polyesters. So let's just look at polyester for a second. Polyester is our first example of a condensation polymer, so let's just put CP beside it to keep that focus in mind. Get rid of that. Let's redo that for a second. Okay, condensation polymer. Now let's talk about this two-handed monomers for a second. So to form polyester, you want to use something like a dicarboxylic acid. So if I just use a general formula here, remember these little skeletal formulas just show the backbone of carbons. It's just a bit neater. So a dicarboxylic acid is going to have a carboxylic acid functional group on one end, and then a second carboxylic acid functional group down the other end. So that's what makes it a two-handed monomer. Alright, so a dicarboxylic acid would be that monomer, and then you would use something like a diol. So a diol, if you remember back to level 2, you can form diols from oxidation of alkenes, and that's the link there. So this would be a diol. General name for it is a diol. Now the actual specific names come from the length of the carbon chain, and then the positions, the number for where the functional group is attached to. This would be a dicarboxylic acid. Dicarboxylic acid. Okay, so your dicarboxylic acid and your diol. So these are the hands. Now just to illustrate this one time, and I won't do this again for the rest of them, but the hands would be that. So that is one hand. If you think about it like that, and that's the second hand. Funny looking hand, but it's a hand nevertheless. And then on the other molecule, I'll just use a different color. On the diol, its hand would be here. So it is little small hands, but it has two hands as well. And if you could imagine, then the hands will then just join together and hold hands, and this is what forms the polymer. Now, to generate this polymer, obviously you can't, well, it's maybe not obvious, but you cannot have those two OH groups joining together without loss of something. So hopefully it's obvious that the small molecule lost here is going to be H2O, or water. So if we then draw the polymer which results from this, the polymer is going to have the general structure of, well, if you remember from the formation of esters, a carboxylic acid and an alcohol makes an ester. So it's the exact same situation here, except that we're forming a long chain of repeating ester functional groups. So there's one, that's an ester linkage. And then it repeats itself and you get another ester linkage, and it will continue and continue. So again, use those brackets and then little n, and that polymer just continues. So this is a polyester because you have many poly, the prefix poly means many, so this is a polyester, many ester linkages making up the polymer, so that's a polyester. And that is also, as we say then, for every time you form an ester linkage, you get elimination or loss of H2O, which makes it a condensation polymerization reaction. Okay, now just to refer back to how do you get from the polymer back to its component monomers, what you need to do here is you need to subject it to hydrolysis, just like with a lot of the other, so we looked at esters being driven back to their component carboxylic acids. It's the exact same idea. You would want to subject it to acid hydrolysis in order to reform the alcohol and the carboxylic acid that formed it. So that is all I'm going to do on the formation of polyester. So a new page now for the second of the four that we're going to cover. So now we're going to look at polypeptides. The polypeptides, for those of you that might be studying level, stay away from that, level 3 biology. So polypeptides are also known in general terms as proteins. And proteins, hopefully it's common knowledge that proteins are formed from the assembly of various amino acids. So therefore, when we're drawing polypeptides, the monomers are actually amino acids. So if we take the general formula for amino acid, it's going to be a central carbon, and all the carbons, central carbons of amino acids are chiral, apart from glycine, which is the simplest of the amino acids. So carboxylic acid, or an amino acid rather, the name is a bit of a giveaway. So an amino acid contains an amine group. Amino, that's where the amino bit comes from. So we're going to have amine here, NH2. Okay, and then amino acid, so the carboxylic acid is the part which refers to the acid. So the amine for the amino, and then the acid for the acid part. And then we'll just use the letter R for the rest of the molecule. Now R is the one thing which changes amongst the 20 essential amino acids, so that's the one component which changes. But this is the general formula for an amino acid, which is more useful to remember. A different color for a second monomer or a second amino acid. Just going to open this one out here, so the amine group would be more useful to draw like this. Again, central carbon, which will be chiral unless it's lysine, and then your carboxylic acid. A mistake on that there. So your carboxylic acid group at the end. Okay, and then we're just going to draw the polypeptide that we form. So let's do that. Black for the first part. So the polypeptide, again, condensation polymerization, we're going to get a carbon double bonded to an oxygen. Then the nitrogen from the second amino acid is going to come joined on here. Alright, and then you'll have the remainder of its molecule, so carbon, hydrogen, etc., etc., and it will continue on that way. And this monomer will continue on that way. Close our brackets, and then N for repeating number of monomers. In a polypeptide, the peptide linkage in a protein rather, is this right here. Now the peptide linkage is exactly like an amide linkage, which we'll find in polyamides that we're going to discuss in a second. But polypeptides are nature's version of polyamides, so they're natural polymers. Okay, proteins are natural polymers, just like carbohydrates are as well, and I'll discuss those in a second. But you'd have many of these peptide linkages, peptide linkage, in which case, when you have many peptide linkages, you have a polypeptide. And then all we need to look at now, so also with all condensation polymers, you form the polymer, plus you have a loss of a small molecule, again H2O in this case. the H2O coming from here and here. Um, so the only other thing now is to discuss the reverse of this process, which again is hydrolysis. So if it's hydrolysis under acidic conditions, then you'll reform the constituent amino acids, and then you're back to where you started. And this process happens. This is essentially digestion. So you eat a protein-rich piece of meat, and then the acids in your stomach will split the peptide linkages and then reform the component amino acids, and then you can reassemble them into some protein which is of use to the body, such as a hormone or an enzyme. Okay, so that's everything I'm going to talk about for polypeptides. Now the next type of condensation polymer I want to look at is polyamides. Now polyamides, these are the main focus for level 3 chemistry, and what they like to talk about in particular is the formation of nylon. Now nylon forms from a specific type of diamine called 1,6-diaminohexane. So I'll just write the name down first of all. So 1,6-diaminohexane. So the situation you have here is you have 1, 2, 3, 4, 5, 6. So 6 carbon chain, and then at position number 1 you have an amine group, NH2, and at position number 6 you have an amine group, NH2. So 1, 2, 3, 4, 5, 6. So make sure I have actual 6 carbons there. So that's 1,6-diaminohexane, which is the first monomer which makes up nylon. Now the second monomer, again we'll use a different color, and let's go with red. And we can use, there are 2 possible monomers that we can use to add to the diamino, and we can use hexane dioic acid, or which is just simply a dicarboxylic acid. So again, a 6 carbon chain, so 1, 2, 3, 4, 5, 6, and we have a carboxylic acid group here and a carboxylic acid group here, and we're adding those 2 together, those 2 monomers together. So this would be hexane dioic acid, or you could call it 1,6 hexanoic acid. So you could call that 1,6. It's a comma 1,6 hexanoic acid. No, get rid of that. So 1,6 hexanoic acid. So 2 ways of naming it. In either case, it's a dicarboxylic acid. This is a diamine, so it's a diamine, 2 amine groups. And with the diamine and the dicarboxylic acid, you're going to form the polyamide in this case. So very similar to polypeptides. The only difference is this is a synthetically produced polymer as opposed to polypeptides, which are naturally produced. So if we draw the polymer, which results from that there, what you're going to have is your chain repeating, then you're going to have the nitrogen group from the diamine, so let's just deal with one end, and then that is going to join on to the carbon of the carboxylic acid or the dicarboxylic acid. So get rid of that. So the carbon is going to be here, and then you're going to have the remainder of the molecule, so let's just draw it like that, repeating itself, and also the loss of, again it's water in this case, so the water is going to come from the loss of a hydrogen, 1 hydrogen from here, and then an OH group from there. That's your water. This group here, again it's an amide linkage. So in a protein it's called a peptide linkage. In a polyamide it's called an amide linkage, the exact same linkage, and the same thing happens therefore if you subject it to acid hydrolysis. You're going to reform the component diamine and dicarboxylic acid. So acid hydrolysis will do that to it. This is nylon, became in vogue just in the, whether it was the First or Second World War, I can't remember which one, but the military used nylon to make parachutes. And then what the women used to do in the in Europe when they found all these old parachutes was they'd use them then to make nylon stockings. So hence the birth of that industry of nylon stockings. And nylon, if you do spill acid on it, then it burns holes in the nylon stockings, which is essentially acid hydrolysis of your nylon. Then with hydrolysis of polypeptides, so again this is a polypeptide, should have written that at the top here. So this is a polypeptide, which is a third type of condensation polymer we're talking about. Polypeptides may also undergo basic hydrolysis. Now basic hydrolysis for a polypeptide results in a slightly different combination of products. So with basic hydrolysis, you're going to initially get so what you have is you're going to have your carboxylic acid. So just do that in red again. So let's just deal with the end of it. So the carboxylic acid is going to be here because there isn't enough protons, there aren't enough protons present. The oxygen initially has a negative charge, in which case if this was sodium hydroxide, the sodium will then join on here and form the sodium carboxylate ion, or salt rather. Just like with the hydrolysis of amides to form carboxylic acids. And then you'll also have your amine, your diamine will just reform here. Okay, so that will reform like that. The with the acidic hydrolysis of a polypeptide, there is a further reaction which sometimes is referred to on exam papers. So initially you may get your you will get your carboxylic acid, and you will get your diamine. But as we hopefully remember, diamines or amines in general behave as weak bases. So if you have a diamine and you have it in acidic conditions, then there's a further reaction which happens, which is as follows. The diamine which has reformed will then immediately react with some of the acid. So let's just put HCl here, and what you'll get is you'll get a charged amine resulting, right? So this will be the ammonium ion, and that extra proton comes from the acidic conditions, and this would not happen in basic conditions. So that's the main difference between acid and base hydrolysis. In acidic hydrolysis, you initially get from the polypeptide back to the full carboxylic acid and the diamine. The diamine then further undergoes reaction with the acid to form the ammonium ion. With basic hydrolysis, you do not have enough protons to reform the full carboxylic acid, and all you get then is the diamine and the sodium carboxylate salt. So that is acid and basic hydrolysis of polypeptides. Okay, the final polymer which I'm going to look at, and just to cover as well, I should mention with polypeptides, you can also form a polypeptide using a diamine and a diacyl chloride. So I'll just quickly write that in blue. So apart from using a dicarboxylic acid, you could use a diacyl chloride here as the monomer. Now this diacyl chloride, hopefully you're picking up at this stage, would therefore have chlorine instead of OH there, and chlorine instead of OH there. And because you're eliminating Cl and hydrogen, what you're going to get is HCl instead of H2O as your elimination. Okay, so that hopefully is a comprehensive cover of polypeptides. As I say, exam papers like to talk specifically about polypeptides, because then they can get into this business of acidic hydrolysis and basic hydrolysis and the difference in the products that you get. And just to complete our review of condensation polymers, the last type are carbohydrates. So carbohydrates, again, these are a natural condensation polymer, just like proteins. The structure of the monomers tends to be quite complicated, and they don't assess you guys on that in level 3. So all you need to remember is a specific example. So let's just go with good old C6H12O6, which is glucose, and glucose plus fructose, TOSE, fructose, will form sucrose. And you also get water, which therefore makes it a condensation polymer. So sucrose is our polymer in this case. That's the small molecule which is eliminated. Fructose also has the same molecular formula as glucose, so hopefully you remember that means that these two are structural isomers, so they have the same molecular formula but just a different arrangement of bonds, so structural isomers. And also to get back then, for isomers to get back from your sucrose back to your component monomers, you want to subject it to hydrolysis, so acidic hydrolysis. And that completes my review of peptides and condensation polymers. It appears just for a couple of pages at the end of the chapter of most level 3 books, and I think it needs to be given a wee bit more focus just because there tends to be a full question on the exam paper on polymers. So take the time to go through this video and then specifically look at acidic and basic hydrolysis of polypeptides. And the other thing they assess you is they give you a polymer and then they try to get you to chop it up into its constituent monomers. So as long as you guys understand this idea of different two-handed monomers joining together to form the polymer, you should be able to identify, split that up and identify that it's made up of something which had that and something which had that on it originally. So there'll be more videos to come, so again, comments are welcome. If anything is a bit confusing, I can redo it, and that should be enough for now. So that's polymers.